So what I'm going to be talking about today is about how the STAN project went from having no users when it was just me and Daniel Lee, who's sitting in the middle of the audience. I don't know if you want to raise your hand, Daniel. Sitting in an audience back to back to where we've got dozens of developers and hundreds of thousands of users. I think one point we knew we made it was when this video appeared. So you can cue the video now. I'll get out of the way. This is from the TV show Billions.
Is that what this is?
Yeah, it's a chance for like-minded users of open source programming language R and data analysis tools like Python, Julia, C++, and Stan to get together and exchange ideas.
It sounds stimulating.
It is.
So basically our people.
Is that what this is?
I want to know who
It's a
they had
chance
as their
for
tech
like-minded
advisor on that
users of
TV show,
open source programming language R
we should
and
send
data
them a
analysis
commission.
tools like Python,
I
Julia, C++, and Stan to get together
So-
and exchange ideas.
Why do we do STAN? Why do we care about statistics, right? Mainly it's because we want to take uncertainty seriously, right? Uncertainty of various kinds just permeates the scientific enterprise, right? We have sampling uncertainty. We only gather finitely many observations or finitely many samples, and our data is finite. We have measurement uncertainty, right? The measurements that we actually take, we point a telescope at the sky and there's angular error, or there's gravitational lensing, or there's bias that comes in based on who actually takes a COVID test, right? And then we have modeling uncertainty in that our models aren't perfect. We might start with something like a Newtonian model and then refine it when we find more data that it doesn't fit. Right? And I like this quote from Bill James, which I stuck in here. Bill James is the famous baseball stats analyst for the Red Sox. And he said that the alternative to good statistics isn't no statistics, but it's bad statistics. So the point is, you're going to be doing statistics whether you like it or not, and you might as well do it right. So what's probability have to do with statistics? Well, probability theory is basically how you use math to quantify uncertainty, right? And in particular, I work in the STAN project is devoted to a kind of statistics called Bayesian statistics. And what distinguishes Bayesian statistics from other statistics is we apply probability theory to everything. We just turn the crank on probability theory, and we use that for data analysis, for estimation and prediction, for comparing different models, for decision theory. We're at a big company, we're at a government, we need to decide what to do. We have uncertainty, we want to propagate our decisions through that uncertainty. Right, so where did STAN come in? It was really approaching the computational bottlenecks here, right? So everyone, well, maybe not everybody, but most people would like to apply Bayesian statistics, but there's two really difficult problems standing in the way. One, you have to be able to formulate your complicated statistical model some way that the computer understands it, right? And the second thing is you have to be able to turn the crank and do posterior inference. Once you have the model, once you've collected data, you want to know what the consequences of that are, right? So I just want to make one more philosophical comment before going on. When we're in the Bayesian world, at least in the pragmatic Bayesian world, which most people are in science, we think of probability as being largely epistemic, that is, about what we know. Right? Laplace said this as well, but I think John Stuart Mill said it the best in the mid-1800s, like 70 or 80 years after Laplace said more or less the same thing, which is that the events can be certain. This was pre-quantum mechanics, of course, so take this with a bit of grain of salt. Every event it's certain is not probable. The idea is if we knew everything, we know what would happen. Right? What we're using probability for is to quantify our uncertainty. Right? Somebody's flipping a coin, we don't know if it lands heads or tails, but if we knew exactly the forces with which it were flipped and could unfold the physical model, we'd be able to predict how it landed. Right? We don't think there's actually uncertainty in the way the coin works after somebody's flipped it. Right? So we're thinking of our probability models as being about what we know. So how does Bayesian modeling go about this? Well, we typically define a generative model. So we have some data y. That might be what we observe, like the positions of the planets in the solar system. Right? And we have some parameters, theta. So theta might be something like the gravitational constant, or maybe unknown masses of the planets. Right? And then typically what we do is we compose a forward scientific model, like maybe we've got Newton's model of gravity that tells us where the planets are, where they're going to be in the future, and a measurement error model. So we're looking at the planets, we may have angular errors, right, in where we point our telescopes, right? We're not going to get exact measurements of where they are. They're going to come with errors, right? Then what we do is we define our present evidence as a prior density, right? So we know something. We know roughly how far away the planets are. We know roughly how fast they're going, right? So there's stuff we know before we collect data, and we roll that in through something called a prior density, right? And the kinds of problems I'm working on, these might be realistic ranges of cancer prevalence, right? We know that 90% of the people in the world don't have cancer of a particular kind. So we have some idea before we start. We know roughly what the possible mass of an exoplanet can be. We know what metabolic rates are so that a person can live pretty well, right? We know that concentrations of particulates in breathable air has to be such that we can still breathe, right? So we have a lot of knowledge going in, and we express that in terms of a prior density. Right? And then for Bayesian inference, all we do is we observe some actual data y, and then we calculate expectations over the posterior, right? So our model is going to tell us, given our likelihood, which tells us the density of the data y given theta in our prior p theta, that defines our posterior, right? Which is the distribution of the parameters given the things that we observed. And then we're interested in estimating parameters. These are all expectations. Right? So the estimate of a parameter in Bayes is just its expectation given the data. Right? This basically goes back to Gauss. Gauss figured out that expectations were great, invented the normal distribution, sort of working backwards from linear algebra and averages. And all that math is what's sort of powering all of this. Right? We do the same thing for forecasting. Is it going to rain tomorrow? Well, we look at all the possible parameter values consistent with it raining and integrate over the indicator function for those, and that gives us our probability estimates. Our predictions for new data are just going to be expectations of the probabilities given parameters. And we can I'm not going to really go into the computation here a lot, because I really want to get to talking about the community and what Stan can do. But we estimate all of this with Markov chain Monte Carlo, or approximate kinds of inference, because basically these expectations work out to big high-dimensional integrals, often over domains that have really complicated geometries. For instance, I have an intern here, Minal Jajaria, who's working with me this summer on transforms and the geometric properties of the transforms. One of the things we're working on, Jim, is SO3. So we're working on orthonormal groups and sort of rotation groups, because we have lots and lots of problems that involve taking, say, cryo-EM, looking at two different poses of a molecule and seeing if we can rotate one to make them look like another. So we know that the parameter we're looking for is a rotation. Right? So what is Stan? I'm here to talk to you about Stan. That was just an introduction to general Bayesian inference, right, at a very high level. So Stan is a domain-specific probabilistic programming language, meaning it's a programming language that was designed specifically to express probability models. It's a probabilistic programming language in the sense that the variables in this model represent random variables, right? A Stan program essentially defines a differentiable log density, right? And the reason we need this to be differentiable is that all of the state-of-the-art inference algorithms involve taking gradients at least, if not taking second-order derivatives and Hessians and dealing with the curvature. So a Stan program defines a differentiable probability model. You declare the data, declare the parameters, define a log posterior, define your predictive quantities, and then we fit models using MCMC for full Bayes or variational inference or Laplace approximations if we want to do this approximately, which we can do at slightly larger scale than we can fit the exact problem. So here's an example. This is a very simple Stan program. This Stan program computes a logistic regression. Right? We basically have data, k is the number of predictors, n is the number of observations, x is our data matrix, y is our data of binary observations. We have a bunch of coefficients, beta, these would be like the weights in a neural network. And then we have a model. We have a prior, very fat prior here on beta. It says it's a Cauchy distribution, right? And then we basically say that y is Bernoulli distributed given the inverse logit of x times beta, right? So this is essentially just a very simple textbook logistic regression. You'd learn it in, like week 2 of your undergrad regression class. This is what it looks like in Stan, right? Now I'm going to show you a really cool application that we just did last week, right? This is actually not my application. This is something Brian Ward and I did. Brian's in here somewhere. And it's implementing this model of David Barmherzig. David Barmherzig's a FRF in CCM, and he's worked with a bunch of people, not just Ju Sun here, but a bunch of people around CCM on these problems, and they're basically biomedical imaging problems, right? In this case, Sounds totally Star Trek, holographic coherent diffraction imaging. Like, I don't know what that, well, I do know what it is now, but like last week I didn't know what that was, right? But it's doing via maximum likelihood estimation, which means it's something we can probably do in STAN, right? Here's a link to the GitHub repo. It's on my organization under CDI. And the reason Brian and I wanted to do this is we just introduced complex numbers into STAN capability, and we just introduced a fast Fourier transform and a 2D FFT. And we wanted to create an application that would showcase how these things were used. Lots of people in CCM do this kind of imaging, so we thought we could kill two birds with one stone. So what does holographic CDI actually involve? Well, step one is you take a coherent radiation source, something like an X-ray, right? And you direct it at some kind of biomolecule, like the biomolecule on the left. I'm not exact, I should have looked up what that biomolecule was. It could be a coronavirus, I don't actually know. And then you have some kind of reference array over here. This is something called a uniformly redundant array. And the idea is that you were going to shoot the beams through both of those things. By having the reference array, it's going to make this whole problem identifiable and going to make the computational problem much more tractable. Right? And we're going to use a beam stop, meaning we're going to occlude part of the beam going in so we don't fry our detectors, and we need to take that all into account. This is just simulated data, but David's shown that this approach works fine for real data too. In fact, I think this is like one of the state-of-the-art approaches to doing this. Right? So what do we actually get in the way of data when we're doing something like CDI? So this is a visualization that Brian did. It's just this is the observed diffracted photon counts on the grid of the sensor. We literally just put some kind of camera sensor behind there, detect photons coming in, right? And you can see the beam stop in the middle of this thing. Let's see if I can get that to work, right? You can see that there, right, which is excluding the low frequencies that you actually get. Right? So this is what the data actually looks like. This is the why we actually observe, and what we want to do is we want to take this and figure out what image would have produced this diffraction pattern. That's the inverse problem. Right? The forward problem is take the image, predict what this is going to look like, but we're doing this the other way around. We get this observation, and we want to reconstitute the image. So what does this look like in STAN? Well, we have to code the data format. This is like the first way we did it. It's gotten more sophisticated to account for a lot of variation in the experimental setup. So the one in the repo is a little more general than this. But it basically is just declaring what we've got, the dimensionality of the image, the registration image, how much padding you want, how big the beam stop is, and the observed photons and the average photons that you're actually expecting. Right? Then we actually code the model. Right? So what we're doing is, well, we have to do a little bit of padding on the data. This is all done with an operation called FFT shift in something like MATLAB or NumPy. And then we have parameters. Right? Those parameters are going to actually represent the image. So the idea is we're trying to estimate X. That represents the image that we've actually got. Right? But our model declaration over here, what this is doing is defining the forward model. Right? And the forward model is being defined really right here. Right? What this is saying is we're taking this padded matrix, which is essentially the biomolecule we're looking at, the registration image, and what we're observing is the absolute value of the two-dimensional FFT of that. Right? So even though XOR pad is a real quantity, the result of applying FFT2 is going to be a complex vector. Absolute's going to map that back to a real matrix, and then we element-wise do the occlusion from the beam stop. Then our observation model is just Poisson. This is essentially saying we have a Poisson process, right, where we have much independence on how these are all, the photons are all arriving independently, essentially. And we have a very simple prior, which just is no prior. We're just assuming this is uniform between 0 and 1 for all of these. Right? Then we just turn Stan's crank. Once we're able to express the model, and the point is when somebody like David writes a clean paper where there's a likelihood defined, we can just pull that likelihood out and code it in Stan like we just did here. Right? And then Stan's inference algorithms are actually really good. So David coded all of this stuff by hand in MATLAB. The Stan implementation, I think, is like 10 or 15 times faster when we coded it this way without even trying to optimize it. Right? So we want to turn Stan's crank to solve it. We can do this in a bunch of different ways. We applied both maximum likelihood, which we do via quasi-Newton optimization, and we also applied full Bayes, which we do with the no U-turn sampler. So David was looking at 256 by 256 pixel images, which what I showed you. Optimization solves the inverse problem in about 2 minutes. We can solve it in sampling about 2 hours. And we're considering L1 and L2 regularizing spatial priors, which I didn't actually talk to you about, but which are very easy. They're like 2-line additions in Stan, right? So what do we get? Well, this is what the recovered images are. So on the left is the true image. On the right is the recovered image. The left is where we're only getting 1 photon per pixel, right? Remember, it's a 256 by 256 image. The one on the left is where, in expectation, we get 1 photon per pixel. The one on the right is a slightly more realistic setting where we're getting about 10 photons per pixel. Once you get above that, shooting more X-rays at the biomolecule degrades it too much. So this is like realistic upper bounds on how much data we're going to get observing a biomolecule until we start doing something much more clever, which is taking multiple pictures and multiple images and starting to align them and build the 3D parts, which are all much more complicated, right? But all the MLE is here, right? What we're showing on the right for the reconstruction is simply the X that maximizes our posterior density. Right? We can also do it with sampling and compute the expectation. By eye, we couldn't tell them apart, so we still have to actually go on and see what works better. So now I'm going to back up after. Oh, and I should say, feel free to interrupt with questions if you have questions as I go along. I'm happy to take questions. Don't give me hard holographic CDI questions because I can't answer those. OK. If there aren't any questions yet, I will go on and talk about Stan itself from a high level, and then talk about sort of how we got to where we're at now. So Stan's available on pretty much all your platforms through all of your standard sort of data analysis interfaces like R or MATLAB or Julia or Python. We now have 40 or more developers. That is, people who have contributed significant features to Stan. We have hundreds of people who've contributed little things, but these are people who've contributed multiple sizable chunks of code. There's probably about 10 full-time equivalents working on Stan at any given time. So this is kind of sobering when I realize that we're putting like, 10 person years a year into this project. It's like we should be directing these resources well. And it's probably more than that, actually, because there's a lot of peripheral activity. The users, hundreds of thousands, although I'll talk a bit later about what it even means to be a user, right? Because that's not really clear. Hundreds or thousands of companies are using this. We know of dozens and dozens of companies, so it's probably closer to the thousands. Downloads, there are millions, but that's half bot, so we don't know how to measure that. The users group is a good indication of how many people are engaged. There's 5,000 people registered for it. Daily, there's around 30 different posts and 20,000 page views on our forums, not counting bots. Those get filtered out of these numbers. There's about 10 books that are written that have Stan in the title and are using Stan as introductory textbooks. There's at least 100 courses that have been designed around Stan and statistics. There's at least 5 where the entire course by 5 different people put their entire course on YouTube using Stan. There's hundreds of case studies out there for different applications, which I think is one of the reasons people like Stan, is they can go find, if they want to do a problem, they can go find a case study for it. That's why we do things like take these diffraction imaging phase retrieval problems and make case studies out of them, because then when the next person wants to do it, they can see what we did and work from there. That turns out to be how almost all of our users work. And if you think about it, that's probably how you work using other software too. There's at least 20,000 articles citing Stan. It's probably a lot more than that. I'll talk about the name later. There's at least 500 papers just using Stan for COVID, because it was one of the major tools used for doing analysis there because of the flexibility it gave you, right? There were a lot of epidemiology packages, but none of them were flexible enough to give you the levers and dials that the epidemiologist wanted for a new pandemic. Whereas Stan's designed to let you design very flexible models very quickly. So was and differential equation-based models, so everyone could do the SIR models and everything else. We've had 4 devoted conferences. Our last conference in Cambridge, UK, had 250 people right before the pandemic. We've been continuing to do sort of littler things during the pandemic online, which have worked out pretty well, but we're hoping to go back to in-person conferences, which have been great. We've taken most of our nonprofit donated money and used it to bring disadvantaged students to our conferences. So each conference, we've spent like $40,000 or $50,000 subsidizing people to show up to the conference, which has also worked out really well. Those students have continued to use STAN, continue to be engaged in the community. People ask me, what is STAN used for? I think it's probably easier at this point to answer what STAN is not used for. It's used pretty much for everything across the physical, biological, social sciences. All 4 baseball teams in the playoffs last year in the semifinals use STAN. They're all recruiting STAN developers to work on baseball stats. People use it in A/B testing at places like Google. It's used all over the place, right? I'll talk a bit more about that, but literally everything, right? And this differentiates STAN from some of the tools that came before it. The tool that's most like STAN that came before it is something called AutoDiff Model Builder, ADMB. That was developed by people in fisheries and wildlife, and I don't think anybody outside of that community ever knew about it. It was like impossible to install. You had to get one of their people sitting next to you. And essentially, it only had users in fisheries and wildlife. I'll tell you how we overcame that problem, which was easy for us. Industries using STAN, again, it's used across industry. It's used for marketing attribution. I went to a meetup in Ann Arbor, and people from Domino's Pizza showed up, which is based just outside Ann Arbor, and said, hey, we're using STAN because we took Google's advertising attribution model, and it works great for us. Like, we don't have the clever analytics people, but we could take Google's STAN model, and hey, it works. Right? And that's what a lot of these people are doing. Demand forecasting. Facebook wrote a very general tool, which hundreds of companies are using for demand forecasting. Pharmacology and clinical trials were being used by all the big pharma things. We were used for COVID clinical trials, mainly phase 1 when you can throw in all the really cool Bayesian stuff. Esports and regular sports analytics, survey sampling, agronomy like computational crop science, sort of one of the things where statistics came from, real estate pricing, basically everything. Inventory management, people are using this for. Why is it so popular, right? So why is everybody using STAN? There's lots of tools out there. There's like 10 competing projects to STAN that somebody could use when they go into this, right? So why are people using STAN? One, and I think really the main reason, is that we have a large, friendly, and open community, right? So that is, people can come into STAN, find examples of the things they want that other people have done in the community and shared and work with that. And we have a very helpful mailing list. People write into our mailing list. People are super helpful, helping them work through not only the statistical parts and how to code STAN, but like every aspect of their problem, right? And you really need to do that to get people going. It's very well documented. I love writing doc. Writing doc to me feels like taking a victory lap after you've done something, and I type very fast because I used to be a secretary and key punch operator back when that was a thing. So I love writing our documentation, but I'm not the only one who's written it. We now have thousands of pages of documentation, including very domain specific, like you want to get into educational testing models. Here's how to apply and get off the ground, STAN for that, right, and so on. It's very robust. We have pretty much industrial strength code with very good user diagnostics. This is important, right? Having stable code that people can rely on is much better than having state-of-the-art code that's somewhat iffy in terms of running it, right? If you want a lot of users and you want your users to come back and not be super frustrated. It's very flexible. The language for expressing models is very, very flexible compared to some of our competitors. And we have a large math library supporting this of differential equation solvers, FFT solvers, all kinds of matrix algebra and things underlying the hood, all kinds of special functions for statistics. Like you can use Bessel functions in your STAN functions if you want. It's portable. to OS language. We've got cloud embeddings that we show people how to use. It's very extensible and developer friendly. If you have a density that you want to use that's not in Stan, it's relatively easy to add a high performance version of that. Not as easy maybe as like Turing.jl in Julia's version, which is one of our competitors that's embedded in Julia. I think they've got about the cleanest interface now. They just have, it's just in Julia, so performance isn't quite there. I know people say Julia is really fast and you can do like, simple iterations, but seriously, if you're writing high performance code, you need the control of something like C++ over your memory, right? It's very hard to do with something garbage collected. Extensibility, right? There are a lot of derived packages. It's very developer friendly. The speed, when I say 2 to infinity orders of magnitude faster, that's over what came before. Since we developed Stan, there's been all kinds of other systems that have come up. Yeah, question? Yes, yes, but I will come back to that and talk a bit about what that means. We don't have as good as GPU support as TensorFlow or PyTorch, but that also goes the other way because they don't have nearly as good a CPU support as we do. So that's an important point, so keep that in mind, we'll come back to it. Scalability was also orders of magnitude better than the stuff that came before it, right? So if you look at something like bugs or JAGs, they were super non-scalable interpreted systems. So when Stan came out, every statistician had these models in their pocket that they wanted to fit, and Stan let them fit them. So there was this very quick ramp-up period where like you get a new disk drive, and then it's all filled up, right? After about a few months, everybody's like, okay, now what can you give us? Now we have the same problem. We just want to fit another order of magnitude bigger model. So your job's never done doing things like this. As big a models as you can let people fit, everybody wants to fit another order of magnitude. Another order of magnitude of data, more granular random effects. We want to look at the effect in subpopulation of coronavirus, not just for everybody. We want to know what happens to elderly people. We want to know what happens to women versus men. We want to know what happens to people who are working every day versus people who are staying home. We want to know what about people living in London versus people living in Wales. We want to have all this fine-grained information. And unfortunately, Stan can't quite fit all of that stuff, right? But really nobody can at this point. So it's not just us. Also, openness. We have very permissive code and doc licensing. Everything's BSD licensed other than like our R interfaces, which are all tangled up with GPL. So I think that's important, and I'll talk about that a bit more later too. Right, so now I'm going to get into a little more about sort of how we got to where we're at and what I think are good steps. Yeah, Adam.
So you said 2 to infinity.
Can you use the mic if you're not?
It is.
Oh, yeah, okay,
yeah.
Great.
You said 2 to infinity. Is that infinity just that there were certain problems that couldn't be solved in any of the previous ones?
Exactly.
And did you focus on Stan being able to do those particular ones? And
I'll talk about that in like this slide.
Oh.
Like the middle of this slide addresses that. Sure. Marcia.
You said PD packages have been included. Do you?
Oh, not internal to Stan. People have linked PD. We have ODE packages.
Which ones?
So we have sundials, which we're using for stiff solvers, and then we're just using the RK45, the Runge-Kutta 4th, 5th order thing from Boost, because that was nice and templated. So when Daniel, the person sitting next to you, and I first coded the ODEs, what we did is we just took the RK45 implementation in Boost and auto-diffed right through it. Right? Terrible implementation, sucked up tons of memory, but as I often stress, it's very good to get something to work first, right? And that worked. Then we could work on adding all the adjoint methods, all the sort of important stuff that's necessary to make it fast, right? But by being able to get it to work, by just pulling in this very general Boost implementation that was fully templated so we could auto-diff through it, that let us build our first big application for Novartis, which I'll talk about in a little while, right? Even before we got it optimized, right? So it's good to get those sort of cutting edge things going. We do have a bunch of people who are working on PDEs, but given that those are so one-off, right, we haven't encapsulated any of them into Stan yet, right? So it's still an open question of like how we could build an interface that would do that more generally. Now, I don't know if Manas was here, but he was asking me about doing one of his solvers earlier, but I don't know whatever happened to that project. So maybe if we take that up, we'll be able to get some cool PDEs in. There's nothing fundamentally stopping it other than the interfaces are complicated. and lack of generality of the solvers. More questions before I go on? Because this is a natural break. The rest of this talk's going to be like yabber, 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 no formulas, no math. I'm just going to tell you why I think Stan succeeded and what I think you should do for your project if you want it to succeed. Yeah. Sorry, I don't know your name yet.
Is STAN an acronym?
No, I should have said that. I'm going to talk about that as well. No, it's named after Stanislaw Ulam, who was the co-inventor of Monte Carlo methods, and Stan the M&M song. Right? The reason it was named after Stan the M&M song is that Andrew Gelman, who we were working with on this, thought it would be cute because I grew up about a block from 8 Mile in Detroit in the 60s when I was a kid. So he's like, hey, you're just like Eminem, and he's got this song called Stan. So I'll talk a bit more about naming later. I think that was not necessarily the best decision we made. But generally, we don't advertise the Eminem contact because I do not want this project to be about me. So what you need, I think, to start a project. So sorry, I should ask if there's more questions before I go on. I'm totally happy to take questions. In fact, I prefer taking questions to just talking myself. So I think it's important when you start an open source project or you start any kind of project that you have a real motivation, not just like, I kind of don't like the way this thing's coded. I think I can code it better, right? And usually that's going to be some kind of pain point that somebody has. So for us, and if you fix that, if you alleviate that pain point for somebody, people will use your tools, assuming that you don't just make it worse. Right? You don't cause more collateral pain, which is often the solution's often worse than the problem in a lot of these cases. So Stan, historically, it's January 2010. I was getting bored working in industry building classifiers for Twitter for another natural language processing application. And Andrew Gelman at Columbia, a well-known statistician, fell into some grant money that some people left for industry and just left in his lap. At that point, he was struggling. He and Jennifer Hill had just written a really cool multi-level regression book. The second edition just came out. But the dirty little secret there is they wrote a bunch of code, and none of the code in their book worked because none of the software they were using was up to actually fitting the models in their book. Right? I think that was a terrible disservice to the field, actually writing a bunch of code pretending it worked when it didn't actually work. Right? But Andrew realized it didn't work, so he thought he would hire a couple computer scientists with industrial coding experience. That was me and Matt Hoffman to try to figure this out, right? So the problem we were trying to solve is, can we come up with a way to express the models in Andrew and Jennifer's book in some general way? So LME4 is linear mixed effects modeling. That's a very popular package for doing this kind of thing in R, right? But it turns out LME4 isn't expressive enough to express all the models in Andrew and Jennifer's books. They were doing like education models, like IRT models, and it turns out that's not just a simple logistic regression. It's got weird nonlinearities in it that aren't just GLM nonlinearities. So you couldn't express a lot of the models they were doing in the sort of state-of-the-art syntax for that at the time, LME4, right? But Matt and I worked with that with Mike Malecki, who's sitting in the audience here today. So we sat around for like 2 months, I think, trying to collaborate and trying to both understand each other's notation, because Matt and I were both coming out of machine learning and computer science, and Andrew's coming out of this long tradition of traditional math stats, and we couldn't understand each other for a month. Right? So a lot of that early sitting around was like several hours a day just trying to come up with a common vocabulary so we understood the problem we were solving. Right? This is a real luxury to have enough money that you can just sit around for months just thinking about stuff, right? But we had that money at the time, right? So Matt and I start working on this problem, right? We're ambitious and busy people, so we started working on this, right? But I want to quote one of my favorite quotes, even though the Henry Ford Foundation has said this is almost certainly apocryphal. So the apocryphal story is that Henry Ford said that if he'd asked his customers what they wanted, they would have said faster horses. Right? If we asked our customers, the people who became our customers, if we asked them at the time what they wanted, they would have told us. In fact, they did tell us. In fact, Andrew told us, he's like, I want bugs to go faster. Bugs isn't fast enough. Like, just make bugs go faster. Right? But Matt spent a long time souping up JAGs. Like, he opened up the back end of JAG, started applying much better C++ programming, vectorizing operations, all the kind of stuff you do if you actually know how to make numerical stuff go fast. And Matt managed to make JAGs go, which is the modern version of bugs, about an order of magnitude faster. It turns out that's not enough. That's just like making faster horses. And JAGs going an order of magnitude faster doesn't help because JAGs is fundamentally using a bad algorithm, Gibbs sampling, that does not scale in dimension. Right? So the problem wasn't that the engineering on JAGs wasn't good enough, it's that they weren't using the right algorithm. At the same time, I'm studying LME4 and filling up notebook after notebook of proposals for language design, and we just can't figure out. They're getting more and more complicated and more epicycles trying to figure out how we can express the models that Andrew wants to express. And eventually I threw up my hands. I'm like, I don't think we can do it by extending LME4, right? So what do we do at this point? We're like, I don't know what to do. So luckily, Andrew has this amazingly popular blog called Statistical Modeling, Causal Inference, and Social Science. There's only one statistical there. That's a typo. It's about everything, even though it's got social science in the title, and Andrew's got a joint appointment with political science and mainly works on that. So like if you were following the last election tracker, The Economist was predicting the election, that was Andrew and one of his grad students' models using Stan being used for that. Right? So this blog gets on the order of like 10,000 organic views a day. So there's probably like 20 or 30,000 people looking at each post that comes out on this, including most of the really good computational stats people in the world, in the Bayesian world, read this blog. So it's like having a direct line to everybody. Right? So I asked for keys to the blog and started asking for help on the blog. Right? So I said, where are we going to get more scalable samplers? Well, word on the street at the time was that we should be looking at Hamiltonian Monte Carlo. The proofs had been done that Hamiltonian Monte Carlo had a better order of complexity. It's n to the 5/4 instead of n squared, but more importantly, it has much better constant factors. Right? But it turns out, we started playing around with that, it is almost impossible to tune HMC to work well in a problem. Right? It's a very, very finicky, that has a couple hyperparameters in the leapfrog algorithm for the Hamiltonian simulation of step size and number of steps, which are super sensitive. Right? So we couldn't figure out how to tune HMC. We're like, well, we can code HMC, but we don't know how to tune it. And oh, by the way, HMC needs gradients. Right? Gradients are easy if you've got something like a normal distribution, but imagine you've got something like a covariance function that's constrained to be positive definite, and you need to take derivatives through this and do optimization in a way that like respects this positive definiteness. That's really hard. Right? So we didn't know how to do that either. Right? So the second pain point, right, which I mentioned, is tuning HMC. I don't know if Barry's here. He's going to hate me for saying really, really. He doesn't like adverbs at all, and I'm using 2 of them. But I don't know how else to say this. It's really, really hard to tune. This time, nobody had any good ideas. We asked on the blog, how do we tune HMC? Everybody's like, I don't know. So Andrew formulated the goal. Andrew's like, well, I know how to tune anything. Right? All we need to do is figure out a metric so that we can maximize expected squared jump distance, because that's inversely related to autocorrelation time, which is basically how efficient your sampler is. Right? And then we needed to tune the acceptance rate, right? Which is something he'd done before for Metropolis with Gareth Roberts and other people. Right? So Matt started thinking at that point, he's like, well, what we want to do is we want to keep going. We want to keep evolving the Hamiltonian, because what we want to do is we want to move a long way in each sample. Right? So we're doing Markov chain Monte Carlo. We've got a sample. We want to take a next sample. We want that to be all the way across the distribution. Right? The way we do that is we actually follow the Hamiltonian. By using the gradients, it keeps us to the typical set. It keeps us to the space where the density times the volume is high, which is where you want to do sampling. So Matt and I built a first version of HMC, and it was like magic. Right? We were just like, once we got the tuning parameters right, we're like, this is just crazy. We can't even believe this works. It works so well. So Matt started thinking about how we could make it efficient, and the idea was we wanted to expand that Monte Carlo trajectory, or expand the Hamiltonian trajectory. So the way Hamiltonian Monte Carlo works is you take a fictitious particle, the negative log density gives you the potential energy, and then you couple that with a momentum. So you think of the particle as having a momentum. Then you give the particle a random shot in some direction, usually with normal noise. And then you follow the Hamiltonian trajectory of that generated velocity that you just generated. right? So you follow the Hamiltonian trajectory, and because you're following the Hamiltonian, it's very good, and the leapfrog algorithm is very good at preserving the Hamiltonian, which means you get a very high accept rate when you're doing Metropolis, which means this algorithm works really well, right? It can move all the way across the density in one iteration. But to do that, it needs gradients, right? The gradients are helping balance you wanting to explore more space, but then getting pushed back to where the density is high. So random steps takes you to explore volume like in Metropolis, and then the acceptance or the gradient sort of pushes you back. And those two things, those two countervailing forces, let you zoom right across a density, right? Which you can't. If you've got a big normal density, you don't zoom across it like this. You have to follow the curvature. Right? So almost all of the mass in a multivariate normal distribution is concentrated in a very thin shell. Right? So the idea is you don't go from one side of the density to the other directly. You have to follow the typical set, which means you're going to follow a very circuitous path to get over there. It's kind of an orbit type path rather than a direct path through the sun. Right? So Matt started thinking about the U-turn idea, but it was a long time. It was months and months and months, maybe like 6 or 9 months before he figured out how to have that maintain detailed balance, which you need. Well, it's a sufficient condition. It's not necessary, but it's the easiest way to make sure you have a sound MCMC sampler. Right? And he added bias to this. So he figured out how to do that, but it still wasn't great. And then he figured out how to add bias to get draws close to half an orbit away from where you started, more like a third of an orbit away, which is kind of optimal if you're estimating both variables and their square for variance. And this was all before we had any users. This was just like Matt sitting away, being the genius that he is, figuring out how to do this. I would say overall, there's maybe one good new sampler introduced every 10 or 15 years. This was the one from the 2010s that was introduced. And now every package is using Matt Sampler. If there's one contribution that's going to last from Stan beyond the software, it'll be the no U-turn sampler that Matt invented. Right? Here's an example of just why. This comes from the paper. Right? So what you're looking at here is you're looking at 1 million Metropolis draws, 1 million Gibbs draws, and 1,000 draws from nuts versus what the target is. This is 2 dimensions of a highly correlated 250-dimensional normal. Right? So we're looking at nuts is getting the right answer in 1,000 draws. Metropolis and Gibbs are not getting anywhere close even after 1 million draws. These are optimally tuned to Metropolis, by the way. This isn't like random Metropolis. So the thing is that HMC, as I mentioned before, is n to the 5/4 dimension. Gibbs and Metropolis is n squared. But there's a nasty constant factor out here based on how much correlation there is in the posterior that HMC is much, much better at. The constant's much better for that than it is for Gibbs or Metropolis, which is why you see this kind of thing. Right? This is like the breakthrough. If we could get this kind of behavior to people's real models, everyone would start using this software. So we knew this at the time. Michael.
You say 2 or 3 sentences about what it means for a method to be O of n in dimension? Like, what is the quantity?
How many iterations it takes to draw an independent sample?
Got it. Okay.
Right. So when you've got a purely diffusive random walk process, it's roughly quadratic to explore. Right. And the directed exploration of HMC that follows the gradient through the Hamiltonian flow is much, much better. Right. You can move, like, basically what happens is Gibbs and Metropolis turn into diffusive random walks. HMC makes directed progress. It's like night and day. Right? So the pain point 3 was derivatives.
Just to follow up on Michael's question, are you including the fact that evaluating the Hamiltonian and its gradient takes order n as well? Is that included in those powers of n?
No, that's just number of iterations.
That's number of iterations.
Not cost per iteration. And Alex is absolutely right. The iterations are much more expensive for nuts than they are for Metropolis and Gibbs. But the point is, it doesn't matter. Gibbs and Metropolis aren't even getting the right answer here. So it's like, it doesn't matter how fast they are per iteration. This was, though, the major pushback we got on Stan, trying to explain to users that we didn't care how fast the iterations were, we cared how fast the expectations converged to the true value, is something that we are still explaining to new users, because they all come in and say, well, Bugs is still way faster than Stan. Look, it runs 1 million iterations in the time it takes Stan to run 10,000. And you're like, yeah, but they don't go anywhere. So, It's like, yeah, you can run really fast with, Fred Flintstone steps before you start taking off. Oh, sorry, was there more on that before I go on? You can read the Nuts paper is fun if you want to read this, and there's been much more analysis of this later. Michael Betancourt has a really nice paper called A Conceptual Introduction to HMC, where he explains why this happens in nice geometric and mathematical detail. He's an actual physicist. Okay, pain point 3, right? So remember, what were we trying to do with Stan? There are a lot of pain out there. We're trying to solve it. How do we do derivatives? So I wrote another blog post. I'm like, we got to calculate derivatives. What in the world are we going to do? Does anybody know good packages for calculating derivatives? And a bunch of people wrote back, oh, there's a bunch of symbolic derivative packages. Oh, you can use finite differences. But somebody wrote back and said, how about automatic differentiation? We're like, we've never heard of that. It sounds like that's just a different word for finite differences, right? So, but I still remember sitting in Andrew's office. Right? You were probably there as well, Daniel. And we did a Wikipedia. We did a search. We're like, what is automatic differentiation? And we popped up this really nice Wikipedia page with something that all the applied math people knew, but none of the computer scientists knew. Right? A few did, but most of them did not. Right? So this was before PyTorch, before TensorFlow, before all the big autodiff frameworks that you heard about. At the time we did this, all the autodiff frameworks were really pretty bad. So we did a lot of autodiff engineering, right? And we wanted to have dynamic gradients. So the way we do, and this was a hard decision, we sat around and thought about this for a month, whether we wanted to go the TensorFlow route. This was before they existed, but there were two different ways to do autodiff, either pre-computing the whole graph statically, like TensorFlow, or doing it all dynamically, like PyTorch. We realized that we were going to be integrating through algorithms that were iterative and things, so we pretty much realized we had to do dynamic autodiff. TensorFlow eventually added a dynamic autodiff that's less performant on top of their other autodiff. So the advantage of doing things statically is you can optimize it more, but it cuts down on your flexibility. So there's like these kinds of trade-offs where we're sitting here with no users back in like 2011 trying to figure out which way is the right way to go. Right? This project could have gone badly had we gone left instead of right along a lot of these decisions, and this was not at all sure. Things could have went the other way with a slightly different person in the room or a slightly different internet search. So Matt and I put our industry background together and engineered a better version of C++ that did better memory management, that did better virtual function calling, that did better memory organization, right? We used basically we didn't know this at the time, but what we did is we optimized it, and we came up with something that's an adjoint Jacobian design. That turns out to be the basis of all the modern autodiff designs, but it was really David Duveneau who explained to us what we were actually doing when we did it. So we did the typical computer science thing of looking at a problem, optimizing it, looking at it, optimizing, and we wound up in a standard place for that. I named the first repo at that point agrad. You may know that a few years later, Duveneau and Ryan Adams and Dougal McLaurin were going to start Autograd, which became the basis for PyTorch. So it was the obvious sort of name to call something at this point because you were computing automatic gradients. I think an important thing with any of these packages when you're thinking about software is that it's often horses for courses. This is something one of my grad school roommates said all the time. After TensorFlow and PyTorch hit the scene, we're like, oh, this is like game over for us. If they've got Facebook and they've got Google engineers behind this, we're just three guys sitting in an office at Columbia. Like, we're going to get steamrolled by this stuff, right? So we immediately started thinking, well, we're going to have to think about alternative backends for our language. We're going to have to plan for the fact when we get overtaken. Well, that still hasn't happened. Right? It turns out that big neural networks can exploit SIMD instructions, single instructions, multiple data, which makes them perfect to sit on top of GPUs or TPUs, which is generalized GPUs with another dimension for tensor processing units. Right? Your typical statistical models aren't of that form. They typically don't involve big matrix multiplications and chains. They involve missing data. They involve different people having different attributes. So it's all random access. None of it looks like big matrix problems. This gives us very different optimization goals. It turns out if you're trying to optimize very heterogeneous operations on the CPU, you don't do the same things as if you're optimizing very homogeneous operations on a GPU. So they went along optimizing their problem, we went along optimizing our problem, and about a year or two ago, TensorFlow did a very careful evaluation of Stan versus TensorFlow, and they found that Stan was about 2 orders of magnitude faster on the CPU, and TensorFlow was about 2 orders of magnitude faster on the GPU. Right? So to come back to your question, they're still way better at GPU code. So if you've got like big GPUable problems, you're much better off using something like Pyro or something in TensorFlow or something like JAX than using something like Stan. But if you have a traditional statistical model, you're much better off using something like Stan. Right? So we're still working on this. Right? Recently, we had an undergrad come in to the project and redo the way we did matrix memory locality. Instead of taking a matrix of values and adjoints, now we take a matrix of values and a matrix of adjoints, so we have memory locality. We didn't quite realize when we started. We were not numerical analysis programmers when we started this. We didn't realize just how important getting matrices in the right order and everything was for like we knew you had to go in memory management order, but we didn't realize just how big a factor this is, like an order of magnitude factor. So we've in the last year made most of Stan's matrix operations about an order of magnitude faster. So we're probably closer to TensorFlow now. So how do you get a point of entry into this world? So you've got an idea, you've got an algorithm, where do you start, right? I think it's very important that you start by solving at least one problem well, right? It's sort of like when you do a PhD, right? You don't do a PhD on the whole field. You try to make an advance in one thing so that you know more than everybody else in the world about your little area. So we were trying to find an area where we could make Stan the best piece of software in the world for solving this kind of problem. Well, we're sitting up at Columbia with Andrew, so of course we're looking at hierarchical generalized linear models. That was our target. That's what he hired us to do. That's what we were going to do. We were just going to do it in a little more generality than we'd originally thought of. Right? Just better solvers for those would be a big win, because this probably accounts for like at least 50% of the work that statisticians do on a day-to-day basis. Right? So we worked really, really hard and focused on an early win for that. It turned out not to come from that. It turned out to come from another kind of nonlinear mixed effects models in pharmacology. So I remember I was talking about when Daniel and I built the ODE solver, it turned out there were people at Novartis listening to what we were doing, and they picked it up and tried to apply it to a clinical trial, a guy named Sebastian Weber, whose name I should have dropped down there, who's one of our better devs, who's done a lot of our multi-core processing stuff, because he's got big ODE problems for clinical trials, for drug diffusions through the body, and they're very hard to solve. You'll be solving like 10,000 ODEs for each density evaluation, because you have 2,000 patients and you need to solve an ODE between each injection they get, which are discontinuities. So Daniel and I spent like 6 months optimizing C++. This was grueling. We were ready to release. We had a version of Stan, the language was working, the transforms were working, the autodiff was all working, and Andrew's like, yeah, we shouldn't really release this until we're really faster than everything else. So then we spent a grueling like set of optimization trying to do everything. So we introduced template traits to drop constant terms, like Daniel figured out how to do that. We introduced vectorizing, sort of views into things so that we could do vectorized operations. Doing that with expression templates. We checkpointed doing like intermediate evaluations. We did analytic gradient unfolding until Stan was faster than JAGS on all of JAGS case study models. Took us about 6 months, but then we were ready. Then we had something that was better than the existing package on every single model that the existing package was advertising that they could do. Right? So then we're ready to release. Then we think we have something people will use. Right? Projects can be very incremental. Like most projects aren't very innovative. Like the pushback we get on this is people are like, well, Stan's really boring, right? It's only doing like some engineering stuff, right? So what is that specifically? They're absolutely right. We really are just doing better. Aside from nuts, which was a real innovation, most of what we've done is just really solid industrial engineering for a problem a lot of people care about. Right? So our autodiff was really based on a system in Trillanos, which is a big like Sandia project called Staccato. Right? Mainly I based it on this because it was one of the only code bases I could understand. The code at the time was just impossible. And our language is a generalized and statically typed version of bugs. Back when I was a professor, I used to do programming language theory on type theory, right? I really like typed programming languages. You really need types to debug when you're making your programs big. It's been a bit of a bottleneck for some of our users, though. And our sampler is really just an adaptive form of HMC. Well, the form that took was pretty innovative, I have to say. So I want you to take all this with a grain of salt. This is all in hindsight, right? We did a lot of this consciously. I can remember what we were thinking at the time, but this presentation's all in hindsight. And it's really, really important to keep this in mind. This requires a lot of luck, especially good timing, right? This project wouldn't have worked had we started it 6 years later or had we started it 10 years earlier. It really pretty much had to be done when we were doing it, and like everybody else, like the forces had come together at that point, which is why everybody was doing it. Marketing and sales. I cannot emphasize this enough. Your project, your papers, they're not going to go anywhere unless you tell people about them and get out there and sell them. Right? Most grad students think they'll do brilliant work and then the field will just pull them in. In fact, the grad students think people are going to steal their work. No, you can't even get people to read your work. It's exactly the opposite problem. Right? But we had Andrew Gelman's blog. This is an incredible platform to get the message out. So we could get the message out to all the people we wanted to communicate with very quickly. Andrew also wrote the standard textbook for Bayesian data analysis, and he was revising a version of it and revised the version to use Stan. Right? So when Gelman puts you in his textbook and blogs about you, people in the Bayes community listen. So I don't know how to give you advice. I don't know how to transfer this advice. We had a huge advantage when we started having access to Andrew's blog and Andrew's support. Right? It would be sort of like if Leslie had a blog that everybody in PDE read and Leslie said, this is the best way to do PDEs, then everybody would start listening, right? They'd go out and try to do that. No? No? I think they probably would. They'd at least try it. They'd at least try your ideas. You just want to get them to try it. That's all you need to do. Right? So we also did a lot of meetups. We did lectures. We did hackathons, everything we could to get the word out. We did lots of 2 or 3 day classes. We were volunteering to go all over the place. Like Daniel and I taught a bunch of these, doing a bunch of classes just to teach people how to use Stan. Right? Why wasn't this done before? Well, as I said, HMC is hard to tune. Hand-derived gradients are like too big of an ass to actually put in everywhere. Autodiff was really primitive. Language and compiler design is hard. Also, all these models involve constrained parameters like simplexes or probabilities or positive definite matrices. These are really difficult. We automate all of that stuff, automate all the change of variables and the Jacobians, and I'm working with an intern this summer, Minal Jajaria, on the comparing the statistical and computational efficiency of the various ways to map RN to the actual spaces that we care about. It's important to assemble the right team, right? We really started with a much better team than anybody had tried to do this with before. Before, all the people who built the tools before us were, for some reason, epidemiologists. Right? The bugs developers said that if they knew how to program C++, they would have been bankers and never even tried to do stats. They were like, they actually wrote this in a paper. They're like, see, we don't even understand C++. It's way too hard. Also, R was a terrible role model at the time as a language in a community. It's gotten better. But we started on day one with 2 crack statisticians. We had Ben Goodrich, who doesn't write a lot but is brilliant, and Andrew Gelman. And we had 3 industrial-trained computer scientists, me, Matt, and Daniel Lee, who's here with us now, right? And we had 2 years of financial runway in the form of grants. A grant just fell in Andrew's lap, which inspired him to go hire a couple computer scientists, right? Turns out, though, if you're in a project like this, you got to keep reassembling the team. The grad students and postdoc comes and go. The software engineers get hundreds of thousands of dollars salary offers and go off to industry. So we need to keep recruiting devs, and we need to ensure project continuity. Pair programming is really good for this. Tutorial onboarding docs are really critical. We're constantly trying to keep those up. It's also important as a community to be very welcoming to your new developers and prioritize new developer contributions, right? Because that's the way you get them excited and keep them working on your project. It's also very important to support individual users. It's really hard. You're trying to build software. You're hoping to get something general. But when you start, you've got to take the time to work with users one at a time, get them through their problems, right? On message boards, at meetups, it's really time consuming. It's rewarding, but it's really, really draining. The nice part is eventually it bootstraps itself. Once you have thousands of people on your message boards, they start answering each other's questions, and you can kind of step back from that, right? But for the first couple of years, you're going to be spending a lot of time answering questions if you want your software. I would also encourage people to go with an open license. I don't think this is as contentious as it was 10 years ago. I think most people are going with BSD or MIT licenses for their open access projects now, right? And one of the reasons we wanted to give it away to industry is I had gone from academia to industry, and when I was in industry, I couldn't use anybody's projects, right? They were all like academic-only licenses or GPL'd or something. So I wanted to make something so that if devs worked on Stan and then went to industry, they could keep using the things they built. We also get cool open source spin-offs like Profit, and they also have donated a lot of cash and a lot of in-kind contributions. Most important thing, I know I've only got like a minute left, code review. Tech manager friend of mine asked me how we do code review. I'm like, yeah, we're not really doing code review. He's like, do it. That was the single biggest quality boost you can make. Don't let anybody push to your repos directly. Code review everything. It has a bunch of good consequences. 2 eyes are way better than 1 at spotting flaws. And really importantly, though, at least 2 people understand at least every piece of code. This is important for continuity. It also keeps you honest when you're coding, right? You want to earn trust through openness. You really want to be nice to people, right? The similar projects to yours are really your allies. They're not your competitors. You want to make friends with them, and you want to bring the whole set of projects up. You want people to do more Bayes, more probabilistic programming. So we're not fighting with PyMC3. We're just hoping more people use both Stan and PyMC3. Right? And if you explain your problems to people so that they understand them, they'll actually cut you some slack. If you explain we're 3 people sitting here in an office, we're going as fast as we can, right? People will be much more understanding. You have to be very careful with comparisons, right? It's very hard to compare software, especially adaptive stochastic systems. And whatever you do, be gracious to your competitors. It will serve you well in the long run. Right? And you need to get evangelists, right? You need to get people out there talking. It's often the people you recruit as early users who you've helped solve their problems will often be big fans and will contribute doing this. You want to grow your process with your project. You want to build your tooling as you go. One other thing I want to say before wrapping up is high-level interfaces are really good. So it turned out people had problems programming Stan. It's hard. They don't like indexes. So we built a bunch of higher-level interfaces. It turns out more people use those than use Stan itself, right? So those can encapsulate whole models or be flexible systems themselves. Governance, I wanted to talk more about governance, but I'm not actually going to have time. Measuring community is very hard. Naming is very hard. Hadley and I tried to convince Andrew that we wanted a name that had 0 hits on Google and wasn't spell corrected. He was dead set on Stan, but it's unsearchable. So we can't tell how many people are using this. Right?